Whenever we talk about our probability, we typically say, oh, there's like a 50% chance, or there's a 20% chance, or something like that. Whenever we're dealing with probability, we're not going to talk about it in terms of percent. We're going to take that percentage away and talk about the proportion. So instead of saying a 50% chance, it would be 0.5. The probability is 0.5. Because 0.5 is 50% if you convert it over to a percentage. 25% chance, we're going to call it 0.25 probability. So it's the same idea. We're just taking our percentage and making that back into a decimal. So with that being said, your probability can only be between 0 and 1. So if you have a 0 probability or a 0% chance of something happening, it is definitely not going to happen. So 100% for sure. Let's see, what could definitely not happen? I will definitely not grow an extra appendage before the end of class today. I feel certain of that. So I'm going to say that there is 0 probability of me walking out of here with an extra arm. Then there's also things that are completely certain. Completely certain that, whenever you think about it in terms of math, it gets harder. Yes, there we go. Yes, there's the probability of 1 that I will be wearing pink today. I know for sure, right? I will be wearing pink today. Thank you. And then everything else is going to be between 0 and 1. So for math, whenever people say that they're 110% committed, we hate those people. Because you can't be more than 100%. Anything over that is not mathematically feasible, or it's going to be wrong. So you can't be more than certain. You can't have more than a probability of 1. You also can't be less than 0. So if you're going through and doing a calculation and you get a negative number for your probability, you did it wrong. If you're going through and doing a calculation and you get a number bigger than 1, you did it wrong. Because you can't be more than 100% certain something will happen. So you can't have more than a probability of 1. And there isn't anything less than not happening. Yes? Yeah, so 0.5 is the same as the 50%, but we're going to talk about it in terms of 0.5. Yeah. So it's the same idea that ranging from 0 to 1 is still us thinking about it in terms of being 0% to 100%. So it's kind of like the weather, whenever they're like the 100% chance of rain because it's raining. That idea. And they don't say 110% chance of rain. That's not possible. It's just 100% chance of rain. It's already raining. So anyway, so if don't get a number bigger than 1 and don't get a number less than 0. And then the empirical probability. So this is where we're at the P of E, where the E is just an event. So we actually already talked about that briefly with the lottery. So the observed number of times that E occurs over the total number of observed occurrences. And this is based on an experiment happening. So we're going to be using this empirical probability with tables that they give us. But it's going to be the number of times that E occurs. So the thing that you want to happen, or the thing you're interested in looking at, how many times that is on top, out of the total number of possibilities. All right, so here we've got the marital status of the U.S. population, ages 15 or older for 2010. This is in millions. Because it's all in millions, we're not going to need to write out all the zeros because they would just reduce. So we've got split between male and female, and then married, never married, divorced, widowed, and then the total out of male, total out of female. And down here we've got the total for each of these categories. So it says, find the probability that a randomly selected person from the table has never been married. So from the table, that's out of everybody, correct? So the probability of never being married so we're trying to figure out the number that weren't married out of all the people that they have in this chart. So how many people were never married? Yeah, so right here, the 74 is what we're after. So we know it's 74 million, but we're just worried about the 74. And then how many people were there total? Yeah, the 242. And then we'll pop that in our calculator. So we got the 74 divided by 242. And then we want it to be a decimal. And we'll go out 3 decimal places. So we're going to go out 0.306 for our probability. Is that okay? Yeah? All right. Go whatever it tells you to. I just picked 3. It will normally tell you. 2 is probably normally enough, but I picked 3. Go ahead and try B and C right quick. All right, so for the probability of being male, what was your initial fraction? The 118 out of the 242. So it's the total number of males out of the total population. And then whenever you put that into a decimal, what'd you get? 488? All right, super. That okay? Probability is fairly easy so far. All right, so the probability that there is a widowed male. So what was your initial fraction? Yep, so 3 out of 242, exactly. So you're looking for the widowed men, or widowed male, is going to be right here. So there's only 3, so it's really 3 million, but 3 out of 242. And then as a decimal, what'd you get? Super. Those okay? All right. I think probability is fun. Hopefully I'll convince you guys. Or hopefully you already think it. That'd be good too. Okay, so for D, let's see if I can get all this in here. So among those who are divorced, find the probability of selecting a woman. So this one is different, right? This is no longer amongst the entire population. It says among those that are divorced, find the probability of selecting a woman. I'm going to give you a second to try it. All right, so I'm going to introduce you to a little bit of notation right here. So I've got the P and then of, so probability of, and then I have woman. This line here is read given. So the probability of selecting a woman given that she's divorced. So the given part is telling you it's not the entire population. It's saying we're only looking in this area, and out of that area, I'm interested in the first part. So out of the divorced people, I'm interested in the women. So that's all that's telling us. So what did your initial fraction look like? Beautiful. 14 out of 24. And then that was going to be about what as a decimal? Correct. So for this one, so it's telling us among those who are divorced, that means we are only looking in this category. So we're only looking there, and we're going to ignore the rest of the chart. Make sure I'm not about to give away E. Yes. So E is a similar idea. All right. So for E, among women, find the probability of selecting a married person. So the among women is the part that they're giving you. You know that's what you're looking at. And then of the women, you're concerned about who's married. So take a second for that one. And if you can, use the proper notation. That would be super. All right. So what was your initial fraction on this one? 65 out of what? 124? So it's telling us we're only looking at women. So we know right away we're just going to look here. Yeah, so this one mixed it up on you, right? So it's telling us among the women. So it's saying only look at the women. That's all. That's the only population or the only part of this we care about. So just look at the women and then find the probability of selecting a married person. So out of the women, then we've got the married ones on top, out of all of the females, out of all of the women. So 65 out of 124 is about what? Because it told you that they were divorced. So now we come up here, the difference. This is going to be one of the, this is going to be where it's going to make you think. So among those who are divorced, so you're only looking at people that are divorced for D. And then for E, you're only looking at women. Yes. So it just happened to be that one category we had totaled down and one category we had totaled left to right. But they can do either way. So whenever they say among those or given that they are, or, anything, whenever they're saying, whenever they're focusing you onto a group, then you only look at that one group to find your information. Okay, so any occurrence for which the outcome is uncertain is called an experiment. The set of all possible outcomes is called the sample space. An event is any sub-collection or subset of a sample space. So the experiment, flipping coins is always the go-to one. Every time you flip a coin, that's an experiment. The outcomes are going to be your sample space. And then the event is any sub-collection. So let's say I flipped a coin twice. And I kept doing it in sets of 2. But I was only interested in getting 2 tails. So I was only interested in tail. Well, the tail is the event that I'm looking for. So I'm going to look how many times that happened out of how many times I flipped the coin twice. Or, since we're going to do theoretical probability, this is going to be our calculated probability. So in theory, what it should be. So that we're not actually having to look at a chart, but your all's examples are fairly nice. They're going to normally give you the sample space. And the sample space, again, is just all the possible outcomes. So for A, flipping a coin. So we're going to flip a coin twice, so 2 times in a row. And then the sample space, so this is the possible outcomes, is head-head, head-tail, tail-head, or tail-tail. So those are all the possibilities. And it's asking us, find the probability of 2 heads. So the probability of 2 heads is going to be what? Yeah, 1 out of 4. Because there's 1 that we want, and there's 4 possible outcomes. So this is going to be a calculated or a theoretical probability, because we didn't actually do the experiment. They didn't give us a chart with the outcome of an experiment. They're just saying, here's the possible outcomes, what's the probability. So 1/4 or 0.25. And some of the time it will ask you for the fraction, so it just kind of depends. We could have left it as 1/4. And then for B, find the probability of the same outcome on each toss. So out of our 4 possible outcomes, yeah, so it's going to be 2 out of the 4. So the probability of same outcome is going to be that 2 out of 4, or just a half. And the 2, the head-head is the one we're interested in, and the tail-tail is the one we're interested in. So the same outcome, so the head-head and tail-tail, so 2 of those out of the 4 is what we're hoping for. Is that okay? All right, I'm going to let you all try 2. I'm going to explain it to you a little bit. So for 2, sample space for 3 children. So the M stands for male, and the F stands for female. And so this is saying if you have 3 kids, these are all the possible ways, like all the different combinations of the genders that you could have. So it's starting with that you end up with 3 boys, 2 boys and a girl, a boy, a girl, and a boy, so on and so forth. So go ahead and do A and B. So A, find the probability of at least 1 male child. And B, find the probability of at least 2 female children. All right, so for number 2, so find the probability of at least 1 male. So the probability of at least 1 male, so greater than or equal to 1 male. First off, how many options are there total? So there's 8 total. And then how many of these have at least 1 male? I'm counting 7. So here's 1, 2, 3, 4, 5, 6. Here's our 7th, so where we have at least one male in all of those. And it's only the 3 females where we don't have it. So the probability of having at least one male is going to be the 7 out of 8. I want to make a point right quick. The probability of all female would be what? Yeah, that 1 out of 8. So the opposite of this, so the opposite of at least one male is no males or all female. These are going to add up to 1, and I realize that this is a really small example, to where we could just went through and counted there were 7, but if this had been a really massive example, then we could have done that the probability of at least one male is going to be the same as 1 minus the probability of no males. And where we need to recognize that no males is the same as the probability of all females. So it's the same thing, just saying it a different way. So no males and all females is the same thing. But our probabilities are going to add up to 1, which hopefully makes sense, right? So of all the possibilities, if you take the probability of all the possibilities and put them together, you're 100% certain, or you have a probability of 1, that one of those will happen. All right, so this is a little bit more. This is me alluding to the next page. For B, find the probability of at least 2 female children. So the probability of having 2 or more females. So we got the 8 on bottom still. How many had 2 or more females? All right, here's 1 for the person that miscounted, and this is what you missed. So here's the 1, 2, 3, and then 4. So we're going to end up with just a half. If I tell you that if you say to me, I'll work for you for at least $10 an hour, you going to work for me for more? Yeah. 10 is your bare minimum. If you say at least, that's going to be your bare minimum. I'll put it in terms of money. For me, that always works. And same as at most. If I say this job pays at most $10 an hour, then it's going to be 10 or less, right? So we don't want the at most jobs. We're hoping for you'll make at least $10 an hour jobs. Once you graduate, at least 20. We'll go ahead and put you guys up a little bit. But yeah, so the at least is going to be that much or more, and at most is going to be that much or less. And then to keep messing with your head, if it says fewer than or less than, pay less than $10 for that job to be done. That means I won't even pay 10. I will pay less than. That might be more appropriate for a garage sale, right? And you go walk up to somebody at a garage sale, and you're thinking in your head, I'm going to pay less than $10 for that. So if they ask you to pay 10, no, you're not going. Now, if they said $9.50, you said, okay, that's fine, because in your head, you're going to pay less than 10. But 10, deal breaker. Same with more than. If you're at the garage sale, and you're the one selling the stuff, I better get more than $10 for that. That means you're not going to take 10. They better offer you $10.01 or $10.50 or $11, but you're not going to take 10. They better offer more than 10. So anyway, so it's kind of, I try to put it in terms of money, and that helps me. But yeah, no, the wording does get confusing. It definitely does get confusing. Are you guys okay on this one? So it's asking you to find the probability of getting 2 numbers whose sum is 4, and then find the probability of getting 2 numbers whose sum is 7. And they were nice enough to give you the chart. So what this is talking about is rolling 2 die. So rolling a pair of dice. And this would be the first roll, and this would be the second roll. Or I guess rolling 1 die twice. So they're just listing the first and second for in this, but you could have actually gone through and just kind of thought about it and figured it out. All right, so let's talk about this again, or talk about this right quick. So again, you're just taking one die, you're rolling it two times, and then you're figuring out what the probability would be of getting a sum that is 4. And they were nice enough to go ahead and give you this little chart here so you can see first roll, second roll, and they just organized it to where you can go through and hopefully fairly quickly figure out which ones add to 4. So so the probability of a sum of 4, out of all these ways, how many of these sum to 4? 3 of them. And then how many were there total? 36. And we reduce that down and get what? Yep. So if you're not seeing it, the sum of 4 is going to happen on those 3. And there's 36 total, so you can get that by either counting them all or just knowing that 6 times 6 is going to be 36. For B, we're going to find the probability of getting a sum of 7. How many of these are going to sum to 7? 6 out of 36, which reduced down to, just 1/6. So the 36, again, that's your sample space. That's all possible outcomes. This is all the possible outcomes. And then as far as the sum of 7, all those right there are going to add up to 7 for you. Okay, so let's talk about the probability of an event not occurring. So this is whenever I was referencing, we were doing 1 minus, and I was like, oh, I'm doing this because of what we're going to be doing in a couple pages. So the probability of something not happening is 1 minus the probability that it will. So if the probability of me randomly picking somebody out of this room and the probability of me getting a female is, seems to be a little bit more of you, so we'll say 0.7. So the probability of picking a female out of this room is 0.7. Then what's the probability of picking a male? Yeah, just 0.3, exactly. Because you're either male or female. So the probability of picking a female being 0.7, we know that the other option has to add up to 1. So the probability of picking not a female is going to be 1 minus the probability of picking a female. So that's going to be your 0 minus your 0.7 or your 0.3. But another way to say not a female is to say male, right? So is that kind of idea? So let's look at this. So we've got our educational attainment in millions of the United States population, ages 25 and over. So this is talking about that they had less than 4 years of high school, that they had 4 years of high school only, so that they didn't graduate high school. They graduated high school, some college, so less than 4 years, or 4 or more years of college. For a randomly selected person described in the table, find the probability that the person, and then I want you guys to find that they have not completed 4 or more years of college. They have not completed 4 or more years of high school. I'm going to give you all a minute to think about that one. And for B, it's not asking you to overthink it. It's just saying all the people that would not be in the category of 4 years of high school. So just assume that it's being straightforward. All right, so we'll talk about A. So the probability that they have not completed 4 or more years of college, so not 4 or more years of college. is going to be the same as 1 minus the probability that they have 4 or more years of college. Is everybody okay with that? Yep, all right. So it's going to be 1 minus, and then what was your not reduced fraction for the 4 or more years of college? Yes, it's one of the two. And what's it definitely over? There we go. So it's definitely over the 174. So it's definitely over this total here. So the has not completed 4 or more years of college. So the has not is the opposite of this part right here. The completed 4 years or more of college. So the 4 years or more is going to be right here. So what's our top number going to be? The 45. Exactly. So the way we're going through and doing it is that we're doing 1 minus that they have completed 4 or more years of college. Because if you were going to actually go through and look at the people who have not completed 4 or more years of college, you would need to add up all of these. So you could either add up all of these or do 1 minus this. And since we're on this particular page, we're doing 1 minus this because we're talking about the complement or the fact that the probability of something happening and not happening has to add to 1. So to get the probability that they have not completed the 4 or more years of college is going to be 1 minus the probability that they have completed 4 or more years of college. It's a little confusing, yeah. Just takes a little thinking, little extra thinking maybe. Yeah, so it's going to be the 1 minus 45. Which is, what's it give me as a fraction? All right, 43 over 58. Is that okay as a reduced fraction? All right, super. All right, and then for B, has not completed 4 years of high school. So what it's wanting you to do is only look at the category of 4 years of high school. So if they've completed the less than, that's okay. And they've completed more than that, that's okay. So they're wanting you to think of this in terms of the probability, so of not 4 years of high school, as being 1 minus the probability of 4 years of high school. So we would only be concerned about this category, so the 4 years of high school portion. So we're doing the 1 minus. They're going to have 1 minus, and then what's going to be the fraction or the proportion for the 4 years of high school only? Beautiful, 56 over 174. Let me make that a better 56. Thank you. Is that okay? All right. Now for me, this one's a little bit confusing because I would have thought of it as 4 years of high school and the less than 4 years of high school being kind of the same idea here. On your test, it won't be anything confusing, I promise. To where it'll be a little bit more straightforward. So like this first one, I think was very straightforward. So if you have not completed 4 or more years of college, then you're going to be these other categories. And again, we could have added up all these other categories or done the 1 minus this one. And again, because the page we're on, we're doing the 1 minus this one. So if you are dealt one card from a standard 52 card deck, find the probability that you are not dealt a king, or that you are not dealt a picture card. And as a quick run over of a deck of cards, so you're going to have ace through 10, or 1 through 10, and then a jack, queen, and a king. The jack, queen, and king will be your picture cards. So there's 13 cards in each suit. And the suits are going to be your hearts, which are red, clubs, which are black, diamonds, which are red, and spades, which are black. So just kind of your quick run through. Obviously, there's 52 cards in there because it tells you that it's a 52 card deck. So 4 suits, 2 colors. Each suit has 3 picture cards, and it's going to run ace through king or 2 through ace, depending on what you're playing. Anyway, so try those real quick. So the probability you're not dealt a king and the probability you're not dealt a picture card. All right, so we'll talk about A right quick. So just wanting us to find out the probability of not getting a king. Well, we could go through and count up every single card that was not a king, and that would give us the probability. But the quicker way is going to be 1 minus the probability that we do get a king. So we've got 1 minus. All right, so how many kings are there in the whole deck? 4. And how many cards in the whole deck? Yep, 52. So the things that we're interested in, out of the total number of things. So the 1 minus 4 out of 52. It's going to be the same as 1 minus 1 out of 13, right? So just 12 thirteenths. Is that okay? All right, so the probability that you are not dealt a picture card, so not a picture card, is going to be 1 minus the probability that you are dealt a picture card. And again, the picture cards are just referring to your jacks, queens, and kings, because they've actually got pictures on them. So let me not do that. So 1 minus, and then what is your fraction for the picture cards? Yes, 12 out of 52. Beautiful. Because there's going to be 3 in each suit, and there's 4 suits. So we're going to have the 12 total cards, and that's going to be the same as 1 minus 3 out of 13. So we're going to end up with 10 thirteenths. Is that okay? All right. Super quickly, I just want us to go ahead, and I did want to work one where we were doing it the opposite way. So the way that you would traditionally do it, so not using the complement rule, not using the 1 minus. So we went through, and the not picture cards. So we would have ace through 10, or that's going to be 10 cards per suit that don't have a picture on them. So the 10 cards per suit, and then I've got 4 suits. I'm going to have 10, 20, 30, 40 cards that are not picture cards. So the probability of not picture. So we got that 40 out of 52. These are both divisible by 4, right? So we're still going to end up at 10 out of 13. And that's what that's going through and counting, which is going to be exact, is going to give you the same answer as 1 minus what we're not after. Is that okay? Yeah. Okay. All right, so let's talk about mutually exclusive events. So mutually exclusive events are things that cannot both happen at the same time. Your age. So if we were to go and randomly pick a person, they would either be less than 20, between 20 and 30, or older than 30. You cannot be in more than one of those categories at any given time. So those would be mutually exclusive to where you can only be in one category. Thank you. An example that would not be mutually exclusive, if we were talking about employed and student. You can be an employed student. So those are not mutually exclusive. If I can pick one person that could fall into both of those categories, then it's not mutually exclusive. So for here, this is dealing with the probability of mutually exclusive events for this first one here. So this would be, again, if I was going through and I wanted to find the probability of randomly picking somebody out of here that was less than 20 or more than 30, what it's saying I could do is just take the probability of the less than 20 people and then add the probability of the more than 30 people. So we'll pretend that there's, we'll make it really nice. We'll pretend that there's 25 of you. So class of 25, and let's say we'll have 10 of you be less than 20. We'll have for the 20 to 30, 20 to 30, we'll say that there's 12 of you, and so for the greater than 30, that's going to leave us, what, with 3? So you guys are going to be a young class. Actually, you guys might be younger than that. Anyway, but that's what we're going to go with. So if I wanted the probability of less than 20 or greater than 30, because these are mutually exclusive, then I could go through and say, okay, well, my less than 20, I'm going to have 10 out of 25 students. And then for my more than 30, I'm going to have 3 out of 25 students. So I'm just going to add those, and I would end up with 13 out of 25. So this would be the probability of me picking somebody randomly that was less than 20 or more than 30. Does that make sense? Hopefully. All right. So things that are not mutually exclusive. So this, again, would be something like student and employed. So you're not necessarily one or the other. In fact, a lot of you are both. So if we have something that's not mutually exclusive and we want to know, so if I want to know the probability of picking somebody out of here that was a student, well, obviously that's 100%. Let's see. How about we could do has children or employed? So that way we don't have a 100% chance because you're all students. So we do the probability of people that have children and then the probability that somebody's employed. You can be both. So if we want to go through, those are not mutually exclusive events. I would take the probability of being a parent. I would add the probability of being employed, but then I would have to subtract out the overlap. So we have those group of people that were parents and employed. They were added twice. So because they're being added twice, we're going to have to subtract out the people that are employed parents. So we're just taking the overlap out. I will briefly mention the set notation here. This U shape, again, is union. So it's weighing the probability and then all of A, and then also it's going to include the probability of B. So it's saying that we're putting those together. And then here, so again, union, so the probability of A happening plus the probability of B happening, and then we're subtracting out where A and B intersect. Are you all familiar with Venn diagrams? Sort of? Okay. If you're familiar with Venn diagrams, this one up here is A and B. So you're adding the probability of A and the probability of B. For this other one here, if this is A and this is B, oops, wrong one. So probability of A, this guy. So I've counted this little area here already. So this, and then plus this. Well, I counted that area twice. So this subtracting the A intersect B literally means we're subtracting where the overlap is. So we're just subtracting that once because we counted it 2 times. So in a Venn diagram, that's what's going on. Helpful, not helpful? And I'll show you guys that a little bit more whenever we get into an example a little further down so I can show you better with visuals. All right, so this one, so you are dealt one card from a standard 52 card deck, and again, here's your deck. Find the probability you're dealt a red 7 or a black 8. Can you beat both of those at the same time? No. So we're going to use the first formula, which is just the probability of being a red 7 plus the probability of being a black 8. So in non-reduced fraction, what's the probability of being a red 7? Yeah. 2 out of 52, because we have a 7 of hearts and a 7 of diamonds. So there's our 2. We've got 52 total. And then a black 8. Yep, same thing. So 2 out of 52, because we're going to have that 8 of clubs and 8 of spades. So we got 4 out of 52. And then we can reduce that down to what? 1 out of 13? Yep. All right, super. For B, the probability you are dealt a 7 or a red card. Can you be both? Yes. So since you can be both, we're going to have to use our second formula. I'm going to give you all a second to try it, but you're going to take the probability of being a 7 plus the probability of being a red, and then subtracting out the probability of being a red 7. All right, so let's talk about this one right quick. So probability of being a 7, non-reduced fraction is what? There we go, 4 out of 52. Because the probability of being a 7, you've got a 7 in each of these. So you're going to have 4 7s in total. And then the probability of being a red card is what out of 52? So it's going to be 26. So we've got 13 in each. Yes. Yes, because it's only asking for the red. So it doesn't care if it's a pitcher or not a pitcher. Yes, good question. So we're going to have this suit and this suit. So 13 and 13. So there's our 26 out of 52. And then before we subtract this part, so we've got the 7s here. So 7s. And then we've got the reds that are here and here. Where's our overlap? Yeah, these two little red 7s, right? So the 7 of hearts and the 7 of diamonds. That's why we're having to subtract that back out. They got counted twice. So now we're going to subtract how many out of 52? 2 out of 52. Does that make sense why we're subtracting that? No. Mm-hmm. All right, so the probability of being a 7, right here, right? These 4 7s, okay? And the probability of being a red card is going to be all the way through here. So there's 13 of probability of being a red, that 13 plus this 13. So we're going to have 26 of those total. But what happened is the 7 of hearts and the 7 of diamonds got counted twice. So because it was counted twice, we have to subtract it out. Once, we have to take out the overlap. So we're subtracting 2 out of 52 because those 7s were counted 2 times. Keeping it over 52, we're going to end up with 28 out of 52. Okay, we're going to keep it that way for just a second. We'll reduce in a minute. So if I were to go through and just look at this picture and figure out the probability of being a 7 or a red and actually just count them all, I would go through and count all my reds first. That's going to be a little faster. That's going to be my 26. And then what I missed. So the black 7s. So 26, 27, 28. So there's our 28 cards that we're interested in out of the 52. If we hadn't subtracted out the overlap and counted twice, we would have ended up with 30. But there's not 30 cards in here we care about. We're only interested in red and 7. And then what's this reduced down to? So 7 out of 13. There we go. All right, let's look at number 2. So a spinner. You're going to find the probability that you will land on an odd number or a number less than 6 for A. And then for B, the probability of getting an odd number or a number greater than 3. All right, so let's talk about A right quick. So to find the probability of an odd number or a number less than 6, we're going to get the probability of being odd plus the probability of being less than 6, and then subtract the probability of being odd and less than 6. So we've got 8 total, right? 8 numbers total. Probability of being odd is what? Yeah, 4 out of 8. And then we're going to add probability of being less than 6 is what? 5 out of 8. Oh, we didn't trick any of you. Okay. So the 4 is just looking at all the odd numbers. So the 1, the 3, the 5, and the 7. So we've got those 4. And then probability of being less than 6 is going to be 5 and below. So good call on that one. I'm actually really impressed you all caught that. That's awesome. So less than 6 is going to be 5 or below. And the probability of being odd and less than 6 is how many? 3 of them, exactly. So we're looking at the numbers 1 through 5. So we're going to have 1, 3, and 5 that are odd and less than 6. So subtracting out that overlap. So we have a 6 out of 8 or 3/4. Is that okay? All right, if you had forgotten that these were not mutually exclusive, or if you've forgotten this formula, so if you just would have stopped here, you would have ended up with 9 out of 8. And you would have known you did something wrong because you got a number bigger than 1. So there's your big hint. If you're doing probability and you get something bigger than 1 or less than 0, you goof somewhere. So always double check that you're going to be between 0 and 1. All right, so probability of being odd is what? 4 out of 8. And then probability of being greater than 3 is what? 5 out of 8. So we're going to have the 4, 5, 6, 7, and 8, right? And then the probability of being odd and greater than 3 is what? 2 out of 8. Because to be greater than 3, you got to be 4 or higher, so it's only going to be the 5 and the 7. Again, if you'd forgotten to subtract the overlap, you would have ended up with a number bigger than 1, so you'd known there was a goof. So we're going to end up with 7 out of 8. Is that one okay? Mm-hmm. So if it's not mutually exclusive, meaning that you can fall into both of the categories. So this is with an or statement. If you can fall into both categories, then you're going to add the probability for each category and then subtract the things that are in both categories. If it hadn't been mutually exclusive and you still tried to use the same formula, so the probability of one category plus the probability of the other category and subtract the probability of the things in both categories, what would happen is that last one, the probability of being in both categories, would be 0. Because if it's mutually exclusive, then you can't be in both. So the idea, back to our age example, so if I'm looking for the probability of somebody less than 20 or greater than 30, I can add the probability of less than 20 plus the probability of greater than 30. And then if I subtract out the overlap, if I subtract out people that are less than 20 and greater than 30, for that there's going to be 0, right? There's not going to be any people that are less than 20 and greater than 30. So that's the reason we're not going to subtract anything there. But if you can only get one formula stuck in your head, get the second one. So get this one here stuck in your head. All right, so let's do number 3 right quick. And by whenever I say let's, I mean you guys try it, and then we'll do it. So the mathematics department of a college has 8 male professors, 11 female professors, 14 male teaching assistants, and 7 female teaching assistants. Find the probability of selecting a random person who is a professor or female, and also the probability of selecting a professor or male. All right, so let's talk about it right quick. So for A, the probability of being a professor or female. So you can be both, and in fact, it tells us that we have some that are both. So we're going to look at the probability of being a professor. We're going to add the probability of being a female. And we're going to subtract the probability of being both a professor and female. So what was the probability of being a professor? 19 out of what? Yeah. And then what's the probability of being female? 18 out of 40. And then the probability of being a professor and female? 11 out of 40. So not reduced, you ended up with what? There you go. So the 26 out of 40, which reduced down to, beautiful, 13 out of 20. Is that one okay? Yeah? All right. That one felt better from where I'm sitting, so good. All right, then we want to look at the probability of being a professor. Yep. Or male. So we're going to have the probability of being a professor. We're going to add the probability of being male and subtract the probability of being both professor and male. So probability of being a professor is what? 19 out of 40. Probability of being male, 22 out of 40. And the probability of being professor and male, 8 out of 40. And what'd you end up with? 33 out of 40? Is that okay? Yeah? All right. Now, last page. All right, so again, the page we were just on, we were using or statements, and we were adding probabilities, and then in the case of not mutually exclusive, subtracting out that overlap. Now we're going to talk about two things happening. So we want an and statement. Whenever it says an independent event, it means the probability of one outcome does not impact the probability of the next. So for instance, in here, we'll assume there's 25 of you, because I'm going to go with an easy number. If I want to figure out the probability of picking a female and picking another female. So if I'm going to pick two of you, and I want to figure out the probability of picking a female and then picking another female. The probability for that second person I pick depends on if that first person was male or female. You guys agree? So if there's 25 of you, so let's say, so we got 25, so class of 25. We'll make 20 of you female and 5 of you male. I think it's different than before, but that's okay. So the first time I pick, the probability of getting a female the first time is just going to be that 20 out of 25, right? So that part is easy. So for the first person I pick, the 20 out of 25. It's that next person where I have to know what I picked the first time. Because if I picked a female, now I've only got 19 left out of 24. Because I picked the person out. If I didn't pick a female, then I'm still going to have 20 left, but still out of 24 because I picked a male. So the probability changed. Those are not independent. Okay? Not independent. Now, if I put whoever I picked the first time, if I put them back in the mix, then it's going to stay the same from one pick to the next. So if I pick somebody and give them $10 and then put them back in and I pick again, then it's the same probability at that point of being the 20 out of 25 both times. All right, so a lot of these types of problems are going to be things like rolling a die, picking a card but putting it back. So you pick a card, put it back, and whenever it says, instead of saying put it back, it'll say with replacement. So you want to pick a card or pick two cards, so with replacement or something like that. So the with replacement means you're putting it back in the mix to where it's free to be chosen again. Flipping coins, things like that are going to be independent events. So the probability of having two things happen. So whatever A is and whatever B is, you're going to multiply those probabilities. So let's look at 1A. So we have a single die, and we're going to roll it 2 times. So we're going to find the probability of rolling a 5 the first time and a 1 the second time. So the probability of rolling a 5 and then a 1 is going to be a probability of a 5 times the probability of a 1. What's the probability of rolling a 5? Yeah, just 1 out of 6. Because there's 6 possible outcomes, 1 through 6, and the 5 is just one of those. And then what's the probability of rolling a 1? 1 out of 6. So we're going to end up with 1 out of 36. 1 out of 36 is considerably smaller than either one of those things happening, right? It should be, because you just kind of, you made it harder to get what you wanted. So to get the probability of a 5 and a 1, you only had a 1 in 6 shot of getting a 5. So there's only a 1/6 probability of getting a 5 the first time. So you have that 1/6 of a chance to get a 5, and then if you get that, then you're going to roll again and try to get a 1, which you only had a 1/6 of a chance. So it's a harder thing to have happen. So that if it's harder, meaning you're adding more and more criteria to it, then you're going to have a smaller probability of it happening. So there's your 1 out of 36. Does that make sense? Yeah. Mm-hmm. The 6, because it's the die is 6-sided, so all your possible outcomes is just 1 through 6. So the bottom is your sample space, or all possible outcomes. So since we have 1 through 6 as possible numbers that we could roll, that's going to go on our bottom. And then the number of things we're interested in, so the probability of rolling a 5, that's only 1 out of those 6 numbers that we're interested in. And the same is true for rolling a 1. That's one possibility out of the 6 possibilities that we're interested in. All right, so for B, we want to find the probability of an odd number the first time and a number less than 3 the second time. So why don't you all take a second and work on that one. All right, so let's talk about B. So the probability of rolling an odd the first time and a number less than 3 the second time, what's the probability of rolling an odd? 3 out of 6. Because there's 3 odd numbers out of the 6 possibilities. And the probability of rolling something less than 3 is what? 2 out of 6. So there's 1 and 2 out of 6. So if we multiply, we're going to end up with 6 out of 36, or just 1/6. Is that okay? All right. And again, the 1/6 is less than the probability of either one of these things happening, which it should be. All right, number 2. So for 2, you toss a fair coin 6 times. What's the probability of getting all heads? So I want you guys to think about that for a second. All right, so let's talk about it right quick. So we're going to flip a coin 6 times. So we have a probability of getting 6 heads. So that's going to be the probability of getting a head times probability of getting a head. Probability of getting a head. Yep, right, 6 times. All right, so what's the probability of getting a head? Just 1/2, right? Because we've got a head or a tail as our probability, or as our possible outcomes. We're only interested in head. So that's each time, right? Yeah. So we're going to keep on, and it's going to end up just being 1/2 to the 6th power. So if you're trying to do the same thing over and over and over again, then you're going to find the probability of that one thing and put it to the power of however many times you want to do it. 64? So hang on just a second. So if we wanted to do the probability, we're rolling a 6-sided die. So rolling a 2 3 times in a row. So with the probability of rolling 3 2s, so the probability of rolling a 2 times probability of rolling a 2 times probability of rolling a 2. What's the probability of rolling a 2 the first time? 1 out of 6. So we can write it, or we could just know, because we want to do the same thing. Whoops. Yeah, don't know. We want to do the same thing 3 times. We're just going to raise it to the 3rd power. So 1 out of 216. Is that okay? All right.